using calculus to compute areas. We're in the plane. I put down my axes, and I have some curves, and I want to find the indicated area. I go to where the points of intersection are. That's where I'm going to start, and this is where I'm going to end my Riemann sum. So I lay down my partition, grab an arbitrary element. We use left hand for our schematic. Calculate my rectangle area over the element. Measure the height on the vertical measuring stick. Measure the base on the horizontal measuring stick. dx is my base, and this is h, the height. And then I sum those from start to end. Base times height. Let's do an example to illustrate. Lay down our axes. And I have two curves. And I want to find the indicated area between these curves. So I do my Riemann sum area construction. I find where I'm going to start, I find where I'm going to end, the curves intersect. So there's my start point for my partition, my end point for my partition, and I lay down partition points. Step 2, I choose somewhere in the element to evaluate the height. We're choosing less for the schematic to make life simple. Step 3, I sum my areas. So to get my area, I need to know what the height is. So I go to the vertical measuring stick, measure the height, and measure the base. Head minus tail, that's the height. Collect like terms. And sum my rectangle areas. There's my area construction. Instead, I'll take the antiderivative, break up sums, pull out constants, so this one's easy, and plug in the start and end points into the antiderivative. This is the fundamental theorem of calculus, this step. I'm turning an area construction into function evaluation. All that's left is to find the start and end point. That's where the height is equal to 0. And that's just algebra. It's a negative quadratic. I'll multiply by a negative sign to make it in the right format for complete the square. Complete the square. Rewrite 7, common denominator. Now x appears once, and I just unwind the function. My start point is the negative square root. My end point is the positive square root. And I just plug those numbers into the antiderivative. Antiderivative at the end point. Minus antiderivative at the start point. That's the answer. Let's do a slightly more complicated example. I'll keep the curves a little simpler for algebra's sake. So here, instead of 2 curves, we'll do 3 curves. Curve 2. And curve 3. And I want to find the area enclosed by those curves. Riemann Riemann sum construction. There's my start, there's my end for my partition, and I lay down my partition points. But now when I start choosing my heights, I notice there's a point in the middle, call it M for middle point, where the height is going to change. The function is going to change. So I have to split it into two cases. The elements on either side of that are different. So I have to do each case. On the left side, bottom curve, top curve, so the height, head minus tail, top minus bottom. On the other side of the M point, bottom curve, top curve, head minus tail, top minus bottom. And now step 3, I sum those rectangles from start to M, and I sum the other rectangles from M to end. Now I've got to find out what these points are. They're the points of intersection, or in this case the point where the height is 0, either way. Plug it in. Here it's the point of intersection. Plug it in. Point of intersection, or where the height is 0 in this case. And plug it in. There's my area construction. I'll take antiderivatives and plug in the endpoints. This is the fundamental theorem of calculus I'm invoking right here. This is the fundamental theorem of calculus. And yes, I do want you to know when you're invoking it. I plug in the -1 and subtract off the lower limit. Plug in the top limit, subtract off the lower limit, and there's my answer.